Previous derivation or expansion of the second law, I feel we are ready to explore our first problem. And here I have like a crude drawing or free body diagram, if you will, of a block on an inclined plane. And so here we see the three forces acting on it. Let me look, I think that looks more like the center. And here's the normal force, here's the frictional force, and here is the gravitational force uh, pointing downwards. Here's the angle theta of the incline with respect to the x-axis. Excuse me. And the problem statement is to find the block's motion with respect to time. That is a grammatical error. Sorry, that was bugging me. But find the block's motion with respect to time. All right, so how can we do this? I usually recommend to choose a reference frame and use one axis or make one axis to be the varying axis. What I mean by that is you see if we kind of like rotate, if we neglect this, we can rotate it, not like that, but never mind, this is a bad program to display it, but if we just consider this to be lying down flat without the morphing of the block, like this, here we'll make that block a little bit more retarded than it needs to be. And this point obviously goes down, and then the gravitational, the gravity vector like just moves, obviously rotates that way. Just doesn't totally mess up the arrow that I had crudely drawn, but anyway, it looks like that. This all the way to the center. That was my poor representation of what happens, but anyhow, we can express that mathematically with the, I guess, the total force of the block would obviously equal the sum of the force on the x, when this is the I unit vector plus the force on the y. Oh, no, sorry, I forgot the unit vector. Unit vector plus the force z, and its adequate unit vector. Now, since it is a two-dimensional problem, we can therefore, I'll make this look like that. We can therefore say that the force z is equal to 0, simplifying our problem to only this. Kind of neat. Here, I'll double space it. So now, since we have rotated this or made it flat, so that our only varying axis, if you might say, is the block is only moving this direction, not downwards and sideways. Now it's only moving to the right, positive to the right, positive to the right. So now what we have to split up are the components, and this is relatively simple. And this, this strictly from the bad drawing, we notice that we have a normal force and a gravitational force acting on it, which will be n minus the mass of the block, just an arbitrary m, times the constant of gravitational acceleration on the Earth, times the cosine of the angle. This is, physics 1 stuff. It shouldn't be too confusing. It should make relatively good amount of sense. And note that the normal force in this case is equal to mg cosine theta. So this conveniently makes our problem, again, much more simple. I want the logic arrow to appear. There we go. We make it so that the force on the y is equal to 0, and that is the beauty of making only one varying axis. Your block is only accelerating, or I don't know, maybe having a constant velocity in the x-axis. We don't have to consider it going up or down. And so now we have to go back to the second law that we kind of toyed with. If you recall, it looked something like, if I recall, right, was x equals, we got, this, and then we got the force over 2m, and plus, we're going to cheat here, we're going to look at the previous derivation of this, v naught t, and I'll post all of these as PDFs, all of these like equations that I have written out, in the comments for y'all to download if y'all want. I want to be as helpful with your physics knowledge as possible. And here we are. There we go. That does not look pretty. There we go. So we recall from previous derivation this handy-dandy equation. And our force on the x is conveniently there. Here, let me rewrite this. For the sake of this problem, our f on the x is equal to oh, my mind totally went blank. Sorry about that. The gravitational force on the x. That makes no sense. But in this case, it does because we modified our axes minus the frictional force. Is that how I wrote it in the diagram? Yes. Like that. And substituting what we know F is equal to a coefficient of friction, or frictional coefficient mu, times mg cosine theta from physics 1. And we know that gravitational force is simply mg sine theta from the diagram. And we can plug this in, getting x is equal to 1, I'll write this like that. So 2 over g, 1/2 g, times sine theta minus mu cosine theta times t squared. And there's obviously no initial velocity. That's why v naught is v naught is 0, so that cancels this out, and x naught is also 0. So I'll make a side note of that. How about we'll put this on a star when v naught and oh, there we go, and x naught equals summary. For this type of block problems or inclined planes with blocks on them sliding down, this is your generic equation or function. Let's see, our position versus time. And you can see that theta is constant. It is just problem dependent or case dependent. G is constant, and well, T is, depending at which point in time you're talking about, will vary your position. Also, mu is constant depending on the material in between them. All of these are constant, and also if you want a more complex answer for, I don't know, more complex problem or different analysis, you can make it even a position function dependent on both theta and time, or angle and time. So obviously, if you move the angle of the incline, if you make it bigger or smaller, that's going to change how your position over time. So anyway, to summarize, in the simple case, theta is a constant, mu is constant, and g is constant, and therefore you get one equation. Also, when the initial conditions are 0. And this is the solution to the simple case of a problem going down, to a block going down an inclined plane. Thank you very much. Please like if this helped you. I hope it was. And I will continue on adding different problems for different cases. Comment if you would like to see a problem done. Also email me if you need any help with solving any problems. Maybe I can do a problem online for you if that problem interests me. So thank you all very much for watching. Comment, like, and subscribe.